Hey everybody. Today we're going to finish up graphing the trigonometric functions. We're going to do secant and cosecant right now and do a quick recap of how the graphing's done. And we're going to look at some examples of where this is used in physics. In our book, this is chapter 6.6 and the physics examples are in 6.7. I'm going to make 6.7 extra credit because if you want to learn about it or use it, you'll do it in physics, which I recommend taking. Physics is a great class. This is Math 154. If you're at a different school, it might be a different number, and your book chapters might be different if you're at a different school. But for us, this is chapter 6.6. And here we're graphing secant and cosecant. All right. And the biggest thing to remember about this, secant theta is 1 over cosine theta, and cosecant theta is 1 over sine theta. And why this is important, wherever cosine theta equals 0, secant theta has an asymptote. That pin's dying. Secant theta has an asymptote. And likewise, sine theta leads, I said equals 0, but I didn't write it. Sine theta equals 0 gives us asymptotes for cosecant theta has. So the easiest way to actually go about doing this, graph sine or cosine, depending on the reciprocal function of whichever one you're working with. This includes the horizontal shifts. After you've shifted horizontally, put asymptotes at the zeros. Then do your vertical shift. The reason why I say this is it changes where the zeros appear on the graph. And you want the zeros, you want the asymptotes to be where the base graph is 0. Then do your vertical shift, lightly sketch sine and cosine. And the easiest way I can say this is graph towards the asymptotes away from the center. And you'll see what I mean when we do this. That's just a verbal description of what we're doing. Okay, pause it if you need to. Okay. So recall, for our base graph of sine and cosine, our 5 marks, we've got 0, pi over 2, pi, 3 pi over 2, 2 pi. Let's write sine theta and then cosecant theta. We'll do them together. And then we'll do cosine theta and secant theta. And we'll do them together. Sine theta is 0 at even multiples of pi. It equals 1 at pi over 2 and negative 1 here, 3 pi over 2. When you flip it over, 1 over 0 is undefined. Pi is undefined. 2 pi is undefined. So cosecant theta is undefined at x equals n pi. Funnily enough, we flip 1 over, that's still 1. We flip that over, that's still negative 1. We do it for cosine theta. Cosine theta starts at 1, goes to 0, then negative 1, 0, and 1. When we flip the ones with ones, they stay the same. The zeros turn into undefined. Secant theta is undefined at x equals n pi over 2, where n is odd. Okay. Let's take a look at their graphs. You ready? We're going to graph sine and cosine, plot asymptotes, or we'll start off with sine, graph sine, plot asymptotes, and then do cosecant. We'll start with that one. Two pi, pi, 0. I know 0 is going to turn into an asymptote, so I'm going to make a dash now. I'm going to put in a and negative a, because really, let's do y equals a sine x. Sine is 0 there. And 1 and negative 1 there. That's the base points for sine. I don't really need to put it in. I just want to mark them because that gives me my asymptotes. I'll sketch it lightly. I'll use bigger dashes here. It's important to note that it keeps going. So this is y equals a sine x. We throw in our asymptotes. And I said, head towards the asymptotes away from the center. So here we're going to do y equals a cosecant x. What I mean by the center is this line right here is the center vertically up and down. So if I'm at this point, or head towards the asymptotes away from the center at the y equals a and negative a points. So here I'm going to do this and that. And I'll do that. and I'll do that. Let me get Desmos up. I wanted you to see this. Because I only drew one set. This is one full period. Note, one full period of secant or cosecant has 3 asymptotes, not 2. Okay. I'm going to get this up and going. I guess I can share it real quick. So let's see, I got it saved under chapter 6 for M154. We'll open it. This is the graph of sine. There's the graph of cosecant. I don't have the asymptotes plotted, but you can see where they're at. This graph equals 0 at pi, all the multiples of pi, and you'll notice if we go up, it never crosses there. It's approaching pi. And so what it looks like, if we get rid of the sine graph, it's just a bunch of u's, upside down u's that are alternating. It's easiest to graph them by doing sine first and then doing little graphing away from the center. Now you'll see, before I shift back, let's take a look at cosine and secant. There's cosine. Same thing's going to happen. Everywhere it's 0, we're going to throw in some asymptotes, and then we're going to Tron cycle away from the center. Okay? So let's go back to our screen and take a look at secant. We'll do this here. We've got y equals a cosine x. Here's a, here's negative a. Two pi, pi, negative pi. So the base graph of cosine starts at a, ends at a. The midpoint's negative a, and we got zeros at the quarter points, which means there. All right. So my quarter points become asymptotes. What color did I make them last time? I kept them as black. Asymptote. 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 And now cosine goes like a hill there. We're going to go away from it. And that's it. Cosine x is very lightly right there. And our red line is going to be y equals a secant x. I am sharing the right thing. Yes. Okay, good. So this is the base period of cosine. And a lot of people just do that. When they graph it, they'll actually just graph those. Let me throw some things over it to block the rest of it. So they'll do that. And they'll do that. Okay? Oops, sorry. They'll do that. There we go. 0 to 2 pi. They'll show that part. I think that's a little confusing. I'd rather see the extra humps like that, so that's how I do it. All right. Let's see what else we got. All right, so that's our base. So what does B do? B has the same impact. B has the same impact as on sine and cosine, as the rest of the trig functions. It changes the period. Changes the period. In fact, A, B, C, and D, they all do the same crap they did before. We've got y equals C plus A cosecant of bx minus d, or y equals C plus A secant bx minus d. A, B, C, and D do all the same crap as before. So when we graph them, we graph the reciprocal function and then pencil it in and do the sketching. So let's just take a look at changing B. Y equals cosecant of 2x. Let's make it 3x. Sine went from 0 to x to 2 pi. Now we've got 0 to 3x to 2 pi. Divide by 3. Okay. So we're going from 0 to 2 pi over 3. And I want 3 points in between. Easiest way to do this is maybe multiply by 2. That way I get a 4 pi on top. Because remember, we had period is 2 pi over b. And here it's 2 pi over 3. But I said use 4 pi over 2b, which will be 4 pi over 6. And that's what happens here, 4 pi over 6. So pi over 6, 2 pi over 6, 3 pi over 6. So here we've got increments of pi over 6. 1 and -1. Sine would normally do this. We'll throw in our asymptotes. And we Tron cycle away from the center. All it does is the B just changed the period. Let's put it all together so you can see a full set of it. Let's do secant. I want to show the vertical shift and stuff like that. I'll ignore changing the period for now. We just changed the period. We showed how that was done. Let's take a look at y equals 1/2 of secant x plus 2. So the reciprocal function would be y equals 1/2 cosine x plus 2. So we got 0, pi over 2, pi, 3 pi over 2, 2 pi. B is not changed. B is equals 1, so there's no change. A is 1/2. And C equals 2. There's no D. So what do we do? Let's plot that. -1 and 1, so we're going to need 1/2 and 1/2. These will be my increments of pi. We've got our half points, our midpoints, and then quarter points. Cosine starts up top, ends up top, and the midpoint's at the bottom. I don't know why I put 4 dashes in there. That was unnecessary. And the quarter points are the zeros. The quarter points become our asymptotes. What did I do? I went down to -1 there instead of 1/2. Did it over here too. Those become our asymptotes. And now that I've done that, now do the vertical shift. Asymptotes, then vertical shift. So we're going to go up 2. So 1, 2, this point goes there. And now if I were to do cosine, it would be like that. Now I'll do my graph off of that one. Now we head towards our asymptotes. And the reason why I wanted to point this out to you, look at the zeros now. Look at the zeros of y equals 1/2 cosine of x plus 2. The blue line. The dashed blue line. What do you notice? It never has y equals 0. Our asymptotes go at y equals 0. And so if we do the vertical shift before we do the asymptotes, we wouldn't even have any asymptotes, and the graph of secant would be completely wrong. Okay? So we would have no asymptotes with vertical shift first. That's the important thing to note right there. It's huge. It matters. It makes a difference. All right, let's get the whole kit and caboodle going on. Let's do the full package on a cosecant. Y equals 2 cosecant. Let's see. 2x minus pi over 3. And let's shift the graph down 1. So if we factor that out, 2 out, we've got a equals 2, b equals 2, c equals -1. So we're going to go down. D equals pi over 6. It's the opposite sign, so we're going to go right. Sine is, we've got 4 pi over 2b, which here is 4 pi over 4 for the period, which is just pi. But this one allows me to set up my marks. Shifting by pi over 6 is a little hard here. We need a denominator of something that matches with these two. So maybe let's get these in terms of twelfths. I'm going to just multiply top and bottom by 3 here. And that one's 2 pi over 12. So let's see. 3, 3, 4. 1, 2, 3, 4. Let's make that 12 pi over 12. So that's the halfway mark. That's 6 pi over 12. And that's a quarter point. $18 pi over 12. A is 2, so we need to at least go up and down 2. And C is going to make us go down another one. So I'm going to put in -3 now. All right. So my points of 0, my midpoint endpoints are there. And peak would be there for the base graph. So I'm going to shift those. They all go right by 2 pi over 12. These are where I put my asymptotes. Okay. Asymptotes go in. So this is my shift right. I put my asymptotes in. Now I'll do my vertical shift. Everything goes down 1. The ones that it really only matters on is those right there. I mean, I can do it here just so we can see it easier. And so now we go towards the asymptotes. Okay. Plot period, shift right or left, place asymptotes, shift up or down, and then graph. What's going on here? Why is my screen not changing? God, how far back was that? It was the last one. I'm not sure why this is not changing. Let me stop sharing and reshare. I don't know if it did it correctly. Let's see what's going on. My program froze up. Let me close the visualizer and re-bring it up. Okay, let me reload it. 1 second while we shift through some technical difficulty. You'll actually get to see how I load this up. So let me do share screen real quick. This is what I see initially. That's what I see. I have to go through and rotate it so that it ends up vertical the way I want it. And then I go through and I change the resolution so that we have it nice and crisp. All right. So I don't know if this showed through while I was doing the video. It's kind of hard to see in the video. So I'll just walk you through it again. We did y equals 2 cosecant of 2x minus pi over 3 minus 1. We factor out b, and then we get this. So we're working with our reciprocal function is sine. We have 4 pi over 2b. b is 2. So we put in 2 for b. We've got 4 on the bottom. And so we have denominators of 4. These are my base points. D ended up being pi over 6. The reason why I shifted to 12 is that 12 is the common denominator. 12 is LCD, least common denominator. So I shifted to the least common denominator. That way, doing horizontal shifts are easier. So I needed a 12 on bottom. I multiplied everything here by 3 over 3 and everything here by 2 over 2. This gave me those 4 points and that. All right. So I plotted those. 3 pi over 12 was here. 6 pi over 12 was here. 9 pi over 12, 12 pi over 12. Okay, we can see all those 4 points. Then what I did my shift right of 2. Everything moved right 2. This point moved right 2. This point, where are we? This point here moved right 2. This point here moved right 2. Now these are where the horizontal shift is taking place. I put them down as red dots. So now we've got our red dots there. I put in my asymptotes. Asymptotes on the red dots that where it equals 0. Then I do my vertical shift of -1. So all my red points go down 1. Then I do my graph. Okay. Let's see if there's an alternative way to do that. Let's take a look at an alternative way to do it. I'll do the same graph. You might like this easier. It's probably actually easier for the secant and cosecant to do it like this. So let's do that again. So sine is normally 0 less than or equal to x, less than 2 pi. Let's replace that with the argument inside. I'm going to add pi over 3 to every spot. To do that here, I'm going to write this. I'm going to multiply this by 3 over 3. This is 6 pi over 3. So that when I add it, I have pi over 3 is less than or equal to 2x is less than or equal to 7 pi over 3. Divide by 2 or multiply by 1/2. And we get pi over 6 is less than x, which is less than 7 pi over 6. These are my asymptotes. 2, 3, 4, 5, 6, 7. We'll make that 7 pi over 6. This is pi over 6. Asymptote is right there. Asymptote is right there for sine, and also the midpoint. Then halfway between them, without writing down what the value is, would be there. This goes up to 2. And then we do our vertical shift of -1. And we asymptote from there. Okay. That pi over 6 is really where I had it was 2 pi over 12, which is where I have my asymptote on my first graph that I did. This is 14 pi over 12, which is where I had another asymptote on the other graph. The midpoint here is 4 pi over 6. Which is 8 pi over 12. And then these, if you really converted them to having these, you really need to shift to pi or denominator of 12 to see where those are at. Okay. That effectively cuts all these. One, 2, 3, 4, 5. This is 5 pi over 12. 6, 7, 8, 9, 10, 11, 11 pi over 12. So another way of doing the secant cosecant without doing the period on sine and cosine, plugging it directly in, finding where your asymptotes are this way, putting them up. You have to recognize the midpoints and stuff like that, but we can go from there. If you need to see more, come to office hours. Okay. Let's take a look at 6.7. .7 is going to be extra credit. It's not going to show up on the exam. This is physics stuff. And it's called harmonic motion. Harmonic motion. So this is what we have. I've got a ceiling. This is a ceiling. And from the ceiling, I have a spring going down. And it's holding a block up. And it's at rest. So this is my block. It's at rest. What I'm going to do is I'm going to pull it down. So I start off, I extend it down. And my block shifts down to here. And when I let it go, it springs up here. Probably gets as high as that. And the spring compresses a lot. And it starts bouncing. Starts bouncing. So if I say this middle point right here at rest is effectively my y = 0 mark, then the point it stops at up here would be A, and where it stops down here is -A. Okay? Now we're going to start off with simple harmonic motion. Simple harmonic motion is there is no friction. The air isn't slowing down or anything like that. So this will cause the spring to keep oscillating. And thus block to keep oscillating. Between negative A and A. Now here, what's going on? We're not doing an X. X is now time after release. So I pulled it down and I release it. X is time after release. So let's just call it T. All right. And we can model this position by, notice that it starts off low. So this is T equals 0. This is T equals later. Notice that it starts off low, goes up high. When between sine and cosine, the one that starts off not at 0 is cosine. So we're going to use cosine. S of T, this is position function. The vertical position is going to equal A times cosine. They say omega T. Or we could do A sine of T, omega T, with some shift. Okay? So pause that, draw that down. You're not used to seeing omega, so how does this relate to other stuff we know? You might be. If you saw this in school, high school, you might have seen this before. Your teacher might have used omega. And it comes from this physics idea. So y equals A cosine omega T. Our period, the period is usually used as capital T, as of a capital time, and it equals 2 pi over omega. Okay? Frequency, which is cycles per second. How many times does it go up and down in 1 second? Frequency equals 1 over T, which is effectively omega over 2 pi. Okay? So that's what's going to go on in 6.7 to start off with. Let's look at an example. A spring is compressed 6 inches. And then released. It takes 8 seconds to complete 1 cycle. And what we want to do is we want to develop an equation that models this behavior. After we do that, find the position at T equals 5 seconds. And let's also find the frequency. Okay. So that's our assignment. That's what we're going to do. We'll pause and let you write it down, and then I want to draw a picture. Okay. So I'm going to do it vertically. We compress it so the spring gets pretty flat. And then as time goes on, it starts oscillating. So this is my baseline in the middle. At rest would be right in the middle. This will give me my t equals 0 mark where I compress it. And it tells me 8 seconds later it's completed one full cycle, which means it's gone down and it's gone back up. This is t equals 8. Okay. This vertical light here is 6 inches, which means when it gets down here, it's going to be -6 inches, assuming simple harmonic motion. That's where we're at. Okay, so we've got, this looks like cosine where A is positive, right? A is positive because it starts off on top. In fact, we're just going to say A equals 6 inches. Okay. Now we know the period. That's one complete cycle. That's 8 seconds. It starts repeating after 8 seconds. But we said period was t, and that equals 2 pi over omega. We need omega. So I've got 8 equals 2 pi over omega. I'm going to multiply everything by omega over 8. On the left side, we just end up with omega because the 8's cancel. Omega's canceled here. 2 over 8 simplifies to pi over 4. So I've got A, I've got omega. The answer to part A is y equals 6 cosine of pi over 4 times t. Okay. B, and that's effectively S of t, or position. At t equals 5 seconds, let's just throw it in. Y equals 6 times cosine of pi over 4 times 5. So y equals 6 cosine of 5 pi over 4. Unit circle word there at the diagonal. That's negative root 2 over 2, right? And we multiply that out. 6 cancels a little bit with the 2 on bottom. Y equals -3 root 2. And that's not really all that helpful because everything else was in inches. So we'll throw that in the calculator. 3 times the square root of 2. 4.24 is approximately -4.24 inches, which means negative means below the base or the at rest. It's below the resting point. Okay. Which makes sense if we look at our picture. If it takes 8 full seconds to do it, half of a cycle would be 4 seconds, which makes these crossing points 6 seconds and 2 seconds. And 5 would be right here. So it should be below, right? Should be below. That's good. That's important that everything makes sense. And finally, part C, we wanted to find the frequency. Frequency is 1 over t, which is omega over 2 pi. Pi over 4 divided by 2 pi. Pi's cancel, and I get 1 over 4 times 2 is 1 over 8. We knew that. Why? Because t equaled 8 seconds. Using the equation right here was the hard way to go. Frequency equals 1 over t, which is 1 over 8. 1 over 8 cycles per second. But I wanted to illustrate what you do with omega and 2 pi because they don't always give you t in a simple thing like that. Okay? That's simple harmonic motion. I do want to point out another way they do this graph is they say this is the ground. There is a box on a spring, and then they compress or stretch it this way. So no friction means kind of like a greased floor. A perfectly greased floor, like it never shifts. And finally, the last thing in 6.7 is simple harmonic motion is unrealistic. Even air slows shit down. So frictionless is unrealistic, but it's a good way to see what simple behavior happens. Over time, friction slows down the spring or oscillation. What we call that is damping. Damping the oscillation or damping the motion. So this is damped oscillatory motion. Or harmonic, oscillatory or harmonic motion. And the equation for it is, we still have there's an amplitude. There's still a cosine omega t in there, because it is going in a sinusoidal wave. But now we multiply it by something that decreases with time. A function that decreases with time but never goes negative. Never goes negative. And equals 1 when t equals 0. We want it to have no impact. When you first starting it, it's not damped at all. E to the negative t. So that's what goes in here. It's a times e to the negative t times cosine omega negative t, omega t. The e to the negative t forces the position to get closer to 0 as t approaches infinity. Now, eventually in real life, the thing is going to stop moving. At least to the point our naked eye is. Everything oscillates at some frequency. If we take a look at how it looks In Desmos, I want to show you what it looks like. So let's switch over there. So this is damped oscillatory motion. This is our normal graph. Okay. There's nothing to the left because t starts at 0. You can't use t in Desmos, so it's x. That would be simple harmonic motion right there, but that's not what we have. So we're going to plot that right there. And what does that do? It causes it to start, it goes down, then it goes back up, but it can't go back up as high because friction. And each time it goes like that and it gets slower, lower, lower, and gets close to 0, but never actually hits 0. I mean, we can get super close. No matter how close we get, it's not actually hitting 0. And what's neat to see about this is if I throw in y equals negative e to the negative x, it's like a little funnel. In fact, it's like a whirlpool sideways, isn't it? Why do I have the absolute value in here? What's going on with that? What's that doing? I did this for a reason. Oh, this is like the distance from the center. Or a bouncing ball. Bounce, 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 and it's slowly the bouncing drifts down to nothing. So that's damped oscillatory motion. I use 4 pi x. We could have just done regular x, but let's turn that off. You'll see it repeats. B is 4 pi. 2 pi divided by b is 1/2. So these are all 1/2 wide. All right, that's it for 6.6 and 6.7. Peace.